Hello everyone, and thanks for watching Edupedia World videos. We turn to the final example in our series of questions done for the time-independent Schrodinger equation, and this is the finite square well. An example would be a potential such that V of x is equal to minus V naught for minus a less than x less than a and 0 otherwise. So for example, this would be an example of a finite square well, where this is x is equal to 0, this is v is equal to 0, this is minus v naught. This is x is equal to a and x is equal to minus a. And in this case, we have three separate regions, region 1, 2 and 3, for which we'll have to solve the time-independent Schrodinger equation. So region 1 will be x less than minus a. In that case, what we'll have is the potential is 0, so we'll have again minus h square by 2m d2 psi by dx squared is equal to e psi, which gives us d2 psi by dx squared is equal to k squared psi, where k is equal to root of minus 2me by h. Now once again, this sort of problem will give us both bound state solutions and scattering state solutions. So first we are going for the bound state solutions, assuming that the energy is less than 0. This is similar to the previous video where we did the delta function potential. If energy is less than 0, this whole term is positive and d2 psi by dx square is k squared psi. And so the solution would be psi of x is equal to a e to the power kx plus b e to the power minus kx. But once again, as x goes to minus infinity, we need a term to blow up, and so the second term has to be 0 because otherwise it will go to infinity. So this turns out to be a e to the power kx for x less than minus a. Then let's look at the second region. Now in region 2, minus a less than x less than a, the equation we'll have is minus h square by 2m d2 psi by dx square minus v naught psi is equal to e psi, because in this region the potential is equal to minus v naught. And this we can write as d2 psi by dx squared is equal to minus L squared psi, where L is equal to root of 2m times E plus V naught by H. So it's the same thing as K, but we have E plus V naught instead of E. And in this case, we have minus L squared psi, so the solution would be sine kx and cos kx or Lx. So in this case, the solution would be psi x is equal to C sine Lx plus D cos of Lx for x between minus a and a. And finally the third region, x greater than a, once again we'll have d2 psi by dx square is equal to k squared psi. So we'll have solution of the form of a, or rather f e to the power kx plus g e to the power minus kx, and in this case this term would come out to be 0. So what would be left would be psi of x is equal to g e to the power minus kx for x greater than a. But now we can use a little bit of a trick to simplify it a little bit further. Instead of having to get all the boundary conditions at both a and minus a, we can see that since the potential is symmetric about x is equal to 0, so will psi of x. Psi of x also has to be symmetric about x is equal to 0. So we can write psi of x in a slightly better form, and that is g e to the power minus kx for x greater than a, d cos Lx for x between 0 and a, and then symmetric about x is equal to 0. So the same as this, psi of minus x for x less than 0. And now we need to do the boundary conditions, which are that psi is continuous at x is equal to a and d psi by dx is continuous. Psi is continuous gives us g e to the power minus ka is equal to d cos of la and d psi by dx. Why is it continuous now? Because we proved in the previous video that d psi by dx will be continuous except at points where the potential is infinite. And in this question, the potential is infinite nowhere, so d psi by dx is also continuous. And this tells us that minus k g e to the power minus ka is equal to minus L d sine LA. And if we divide these two equations, the result we will get is k is equal to L times tan of LA. Now what do we have here? We know that k is equal to root of minus 2me by h and L is equal to root of 2m times e plus v naught by h. So the only unknown here is e. So in terms of e, we have actually solved this equation because a is a known, m is a known, h is obviously a constant. But this is as far as we can go using basic mathematics. After this, you have to input it in a software and try to solve it computationally because this cannot be solved directly. So we'll not go into too much detail in this. This is as far as we go. The important thing is knowing how to calculate psi of x for regions 1, 2 and 3, how to use the fact that v0 is symmetric to get this symmetric wave function here. And then using the boundary conditions, the psi has to be continuous everywhere. So we use that it is continuous at x is equal to a. And d psi by dx has to be continuous everywhere, which means it is also continuous at x is equal to a. And when we say that it is psi of minus x for x is less than 0, then automatically the boundary conditions will also be met, meaning psi will be continuous and d psi by dx will be continuous at x is equal to minus a as well. So this completes the bound state solutions. We'll not write the wave functions explicitly, but this is all that you need to know. Now let's move on to the scattering state solutions. And scattering state solutions are those for which E is greater than 0. So once again, let's start with the region x is less than minus a. We have the equation minus h square by 2m d2 psi by dx square is equal to E psi. But in this case, E is positive. So what we'll get is d2 psi by dx square is equal to minus k squared psi, with k being equal to root of 2me by h. And because we are talking about scattering states, we'll do the problem which is similar to the problem we did in the delta function well, which is a wave comes from x less than 0 and then is both transmitted and reflected. So we'll write the solutions not in terms of a cos kx plus b sin kx, but rather we'll write psi of x is equal to a e to the power iota kx plus b e to the power minus iota kx. In that case, a is basically the incident wave, b is the reflected wave. And now let's look at inside the well, meaning minus a less than x less than a. In this region, what we'll have is minus h square by 2m d2 psi by dx square minus v naught psi is equal to E psi. And from this, what we'll get is d2 psi by dx squared is equal to minus L squared psi. But since we are only looking at scattering state solutions for A, B and F, in this region within the well, we'll write it as A cos kx plus B sin kx, or rather psi of x is equal to C sine of Lx plus d cos of Lx. So this is for x less than minus a, this is for minus a less than x less than a. Now let's try to do for the third region, x greater than a. This will be similar to the first region, a e to the power iota kx plus b e to the power minus iota kx. Wait a second, I forgot to write the value of L. L will be root of 2m times e plus v naught by h. So L is greater than k. Now back to this, for x greater than a, we'll have a similar solution to this, except we'll take minus iota kx term to be 0 because we want an incident wave, a reflected wave and a transmitted wave. So in this case, we get psi of x is equal to f e to the power iota kx for x greater than a, and f is the transmitted wave. So let's just write these three again. Psi of x has the values a e to the power iota kx plus b e to the power minus iota kx for x less than minus a. Then it has the value c sine of Lx plus d cos of Lx for minus a less than x less than a, and then it has the value f e to the power iota kx for x greater than a, and we have the values for k and L. K is equal to root of 2me by h, L is equal to root of 2m times e plus v naught by h. And now we need to apply the boundary conditions for x is equal to minus a and x is equal to a. So psi is continuous at x is equal to a. This gives us, in terms of c sine of La plus d cos of La is f e to the power iota ka. So c sine of La plus d cos of La is equal to f e to the power iota ka. Similarly, psi continuous at x is equal to minus a gives us minus c sine La plus d cos La is equal to a e to the power minus iota ka plus b e to the power iota ka. And similarly, again, because the potential is not infinite anywhere, d psi by dx will also be continuous at both these points. So we have d psi by dx at x is equal to a, and what this gives us is L times c cos of La minus d sine of La is equal to iota k f e to the power iota k. So we can see the mathematics turns out to be a little bit more involved in this case. Finally, we have d psi by dx continuous at x is equal to minus a, and this gives us L times cos La c cos La plus d sine La is equal to iota k times a e to the power minus iota ka minus b e to the power iota ka. So this is it. We have 5 variables, we have 4 equations, and that is fine because we just need to find the ratios. Now I won't solve this completely because obviously the mathematics is quite complicated. I'll just write down the final solution, and if you're interested you can solve these on your own. What we are interested in finding is the reflection coefficient, that is mod b squared by mod a squared, and the transmission coefficient, that will be mod of f squared by mod of a squared. So once we find the transmission coefficient, reflection coefficient will simply be 1 minus the transmission coefficient. So I'll write what the transmission coefficient comes out to be. The transmission coefficient comes out to be 1 plus v squared by 4e times e plus v naught. So this is v naught squared multiplied by sine squared of 2a by h root of 2m times e plus v naught whole to the power of minus 1. And the reflection coefficient is simply 1 minus the transmission coefficient. And the interesting thing here is there are certain values whenever 2a by h into root of 2m times e plus v naught, let's say en for an nth case, whenever this is equal to n pi, this term is 0, which means the transmission coefficient is 1. And this is something which we never see in the classical case, but we've seen in the quantum mechanical case, that if you have a perfect value of energy in V naught, if you give the exact right energy to a wave, then it will completely be transmitted, not be reflected. And the graph of the transmission coefficient versus energy comes out to be something like this. If this is the line t is equal to 1, then initially when there is no energy, it is 0. And then at some point it becomes 1, then comes down, then becomes 1 again, comes down, 1. And this is the way it goes. And this phenomena has actually been observed experimentally, and after the hydrogen atom, this was one of the major confirmations of quantum mechanics, especially the theory of quantum mechanics, that if you give the perfectly right energy such that this statement is true, 2a by, of course this is a combination of energy V naught, h, mass and a, which is the half of the width of the square well. But if this perfect combination is equal to n pi, then the whole wave is completely transmitted, none of it is reflected at all. And if the transmission coefficient in those cases is 1, then obviously the reflection coefficient is 0. And this has actually been observed experimentally. So we've solved the quantum mechanics equation, the time independent Schrodinger equation, for a number of cases. We started with the infinite square well, then we did the harmonic oscillator, the direct function well, the free particle, the finite square well, and now what we'll do is in the next video we'll go back to the basics. And right now we've learned quantum mechanics in sort of a sideways way, where we just found out how to get the value of probability density, for example, as mod psi squared, but I didn't give you a proof of that, or I didn't give you a proof of the fact that stationary states, a linear combination of stationary states, is the general solution. We'll put this all into a much more elegant mathematical formulation, and the topic for the next few videos will be linear algebra, which is a purely mathematical topic. And then we'll learn how to solve these quantum mechanical equations. It won't take a lot of time, it will be very quick, in terms of linear algebra. Linear algebra is the mathematical concept which is the language of quantum mechanics. Everything in quantum mechanics is based on linear algebra, and that is the mathematical concept which we'll start in the next video. Thank you.